In this video, I'll be explaining tax theory of my automata theory, Mason practical. Tax theory focuses on mainly on deterministic. Sorry, uh, let me just go back to the question. Sorry. So that's tax theory mainly focuses on non-deterministic finite automata or NFA and how we can work with NFAs using transition tables, state eliminations, regular expressions, the extended transition function, and subset constructions. These are the specific requirements given in the practical. And so after being able to discuss the questions, I think we'll have a better understanding of what you're doing in here. So, like I said, I mean, you all know my name right now. I don't want to be repeating my name, but anyway, my name is Juma Stanley Blacks, and it index number is 2425402029. I don't have to be. Yeah, sure. Anyways, so let me just go on to. Get. Let's just get ready to the work itself. All right. So let's continue. Okay. I need to go back to the question. So we are using this. Right. So let's get back to it. And so the question says that produce the transition tables for the following for the NFA above. NFA is above. So with this, you all know that the definition for NFA. And NFA, well, I think it's just simple. We all know the importance of the NFA, importance of the difference of NFA. I don't know if I want me to do it. Yeah. So for NFA one, the states are Q0, Q0, Q1, and Q2. With the initial state for the NFA1 to be Q0. We all know that this arrow is pointing to Q0, and then that tells us that Q0 is the start state. And then we look through to see what the double circle is. And then we can see that it's on Q2. So Q2 is the accepting state. And now the question is clearly telling us to provide or to produce the transition tables. And so let's provide a transition table. When you're at Q0 and you receive an input of 0, I mean, where do you go? You still maintain your position, right? Because it's a self loop. Look at the top. There's 0 here and there's 1 here. But let's just do the 0 for the meantime. You receive an input of 0, where do you go? You still maintain your position because of the arrow, right? And so if you're at Q2 again, sorry, Q0 and you receive an input of 1, where do you go? You clearly see that you receive an input of 1. You can go to Q0 or Q1 at the same time. That is why the state here, the 0 and then the 1. I mean, you clearly all know why. In the previous video, we talked about this. So if you've forgotten, kindly go back to watch the to watch the. But anyways, I know my lecture knows this, so the video was specially made for Mr. Wonder. Yes. And so if you're at Q0 and then you see an input of 0, where do you go? You still maintain your position. That's what we did. So Q0. If you're at Q0 and you see an input of 1, like I said, you go to Q0 and at the same time you go to Q1. Now let's go to Q1. If you're at Q1 here, receive an input of 0, where do you go? You go to Q1 or Q2 because this Q1 is a self loop and it also goes to Q2. And if you're at Q1 and you receive an input of 1, you maintain the position, right? And so this Q2 here is the accepting state, and basically that's what we have done here is the accepting state, and we use asterisk or the star sign here to demonstrate or to tell the person that, or the person automating the machine that the Q2 is where the accept state is. And so Q2 because 0 and 1 still point to Q2 at the same time. That is just the term that you'll be using. You understand that? Yes. And so Q for the second question, 1 the transition table also represented using the set of sets because multiple states can be possible after reading an input. And so it's just the same thing that we did, right? So I will quickly just go to part B for us to continue. that'll be A. So part B says, using the state elimination approach, convert the NFAs above to regular expression and draw the resultant automata after each state elimination. Yes. Sorry about that. Just give me a second. Just want to have a proper view of what we're doing here. Right. So part B, state elimination. Next, I use a state elimination method to convert each NFA into a regular expression. The purpose of state elimination is to gradually remove intermediate states while preserving the language accepted by the automation. For NFA1, we all know the structure of the NFA1. I first introduced let's use this. I first introduced a new start state called the QS, right? So with an epsilon transition to Q0. I also introduced a new final state called QF, right? Called QF with an epsilon transition from the original accepting state. Yes, that's what I did in this question. And so I then combined parallel edges where necessary. The first states are eliminated is Q0. After eliminating Q0, the transition table QS from QS to Q1 becomes star 0 plus 1. The star 0 plus 1 represents any number from zeros or ones. Any number of zeros and ones followed by a 1. Next, I eliminate Q1. This produces the transition Q0, or you want me to start again? If you want me to start again, then star. You bring your star 0 plus 1, 1. Because of this, the 0 plus 1, star 0 plus 1, 1, and then 0 plus 1, then 0, right? Then 0. Then I finally eliminated the accepting state Q2. The resulting regular expression for NFA1 is star 0 plus 1, 0 plus 1, 1, 0 plus 1, 0, 0 plus 1, then yeah, that is it for now. This expression describes binary strings containing at least 1, 1 followed later by at least 1, 0. So that's what we did in here. Yeah, so that's what we did. Yep. So after getting all this, and then I'm forgetting about NFA2. The same state elimination procedure after eliminating Q0 and then Q1, the final regular expression becomes something like 0. Look at this. It's 0 plus 1, then 0 plus 1, 0 plus 1. That is 0, 0 plus 1, 0 plus 1, 1, 0 plus 1. That is how it is. So the important idea here is that although the intermediate automata change as states eliminated, the language represented by the automation remains the same. That's all that we are saying in here. And then the question C says that part C says produce the transition table for each obtained automata after state elimination. Now let's go back to this. I did it just behind it. And so if you are using this formula to find the transition, I hope it's transition table. Oh, sorry, I'm coming. So transition table. If you had Q, so that's what I did. Yep. After each state is eliminated, I record the remaining state and transition. For NFA1, after eliminating Q0, the important transition becomes QS, then maps on to Q1, which is equal to 0 plus 1. After eliminating Q1, QS maps onto to Q2, which is 0 plus 1, 0, 0 plus 1, 1, 0 plus 1, 0. After eliminating Q2, we obtain a final regular expression. The same process is followed for the NFA2. For this, it's just something simple. I mean, you've done this for a lot of times for us to, if you had Q0, if you had TA, if you had TA, if you had Q0, if you had TA, if you had TA. So if you had Q0, receive an input of, if you had QS, you receive an input of the epsilon. Where do you go? That's what you're doing here. It's like epsilon transition, like, and things like that. So that's what we did for the same NFA2. Exactly. Let's go to question C. Question D. Identify three strings that the first NFA accepts and describe the processing of the strings using the extended transition functions. This video is becoming long. Right. So part D, yeah, we next identify three. We identify. Sorry, I did myself. Identify three strings accepted by the NFA1 and retrace their processing using the extended transition function. Right. Sorry. Yes. So that's what we're doing here. So starting from the first string is 1 0. If you look carefully, you can see that this. You say that the first string is 1 0. Why do you say the first string is 1 0? Because starting from Q0 in the question, we are using the NFA question to answer. Starting from Q0, you can clearly see that if you had Q0 here, the Q0 here, you receive an input of 0. You let's just put the string down. Did I say 10? Yes, I said 10. It's 1 0. So if you receive an input of, we are saying the string is 1. Let's just check it out. If you have Q is 0, you receive an input of 1, you go to Q1. And then since you had Q1, you receive an input of 0, you go to Q2. And what does Q2 means? Q2 clearly state that is the accepting state. Is that not it? Since Q2 is the accepting state, the string is accepted. The second string is 0, 1, 1, 0. 0, 1, 1, 0. Why do you say there is 0, 1, 1, 0? Because the machine can process it as, if you had Q0 receive an input of, if you had Q0 receive an input of 0. Now let's jot it down. 0. 0, you maintain your position. 1, then 1 again, then 0 to the accept state. So because now that's what we are doing. So because the computation ends in Q2, 0, 1, 1, 0 is accepted. The third string is 1, 1, 1, 0, 0, 0. Now let's look carefully. If you look at this, you just transition, just 1, 1, 1, 0, 0, 0 is also accepted. It's also accepted by the machine. So the machine process the input by remaining in the appropriate state until it reaches Q2. After reading reading a 0, it then remains in Q2 while processing the remaining zeros. Therefore, 1, 1, 1, 1, 1, 1, 0, 0, 0 is also accepted. These examples demonstrate the purpose of the extended transition function. Instead of processing just one input symbol, the transition allows us to describe the processing of the entire string. Yes. Right, let's go to part E. Describe the language of the NFA using the set builder notation. Right, describing the language of the NFA using the set builder notation, right? So from the behavior of the NFA1, we can identify its language as the L, right? The NFA1 equals to the function, in simple terms, This means the NFA accepts all binary strings that contains at least 1 1 followed by at least 1 0. For example, the 1 0 is accepted because 1 occurs before the 0. Likewise, 1 0 1 1 0 is accepted because there is a 1 followed by later by a 0. That's what we are saying here. Let's go to the last question and then we end the video. So convert the first NFA into an equivalent DFA using the subset constructions. So that will be the last part, right? So subset construction. Finally, I convert NFA 1 into an equivalent DFA using subset construction method. The key idea behind subset construction is that unlike DFA, a state representing one state, a DFA state can represent a set of NFA states. We begin with a equal to 0. A equal to 0. Then for A we input, and if we receive an input of 0, it goes back to where to Q0. Since A is still since A equals to Q0, you maintain your position. For input of 1, it goes to B. But let's not call the B function for now. For input of 1, A goes to Q0, Q1. So record this new DFA state as B. B equals to Q0, Q1. Q0, Q1. Now, if you had QB and receive an input from B, an input of 0, the possible NFA state is Q0, Q1, and Q2. So we call this C. That's why we have C equals to Q0, Q1, Q2. Right? That's why I have C equals to Q1, Q2. Since C contains Q2, which is an accepting state of the NFA, C becomes an accepting state of the equivalent DFA. The final substate construction table is therefore, let's look at the table. The Q0 is equal to 0. A equals to 0. B equals to Q1, Q2. And the C, which is the accept state, is Q1, Q0, Q1, Q2. So that's what we did here. So A receive an input of 0, maintain A. A receive an input of 1, you go to B. B receive an input of 0, maintains, you go to C. B receive an input of 1, you still maintain your position. C receive an input of 0, you go to C. C, you receive an input of 1, you go to C. So the NFA has successfully been converted into an equivalent DFA. Well, that completes task 3. The main concepts demonstrated here are NFA transition tables, state elimination, regular expressions, the extended transition functions, languages, description using the set grid annotation, and subset constructions. Thank you very much for having some time for this video.